how should I say this? If you have a curve or a fan-like or exponential pattern, when you plot those residuals against your predictors or your independent variables, your x's, then the relationship may not be linear. So there is where you might need a semi-log transformation. Now, if there is a systematic pattern, like you see a clear curve, then you're saying that the model is not capturing the true relationship. So you don't want there to be a pattern. You want there to be kind of like a random shotgun blast of data. Because if you see a very clear, distinct pattern, that could potentially mean that your Y is may benefit from a log transformation. You do have some signs of heteroskedasticity because you have the circumstance here where the variability of any given variable here is it's unequal across this range of values that you see for the second variable, right? That predicts it. So in this scatter plot, you can actually observe the spread of the data points, and you can observe the spread increasing. Ideally, it's great that you bring this up. Ideally, in a perfect world, you would have a three-way split, not a two-way split. So that will give you a development set, which would consist of your training data. So you're training this model on the data, right? It would also have your validation data. That's another, so that's 60% training. And this is an example, 20% validation. And then that gives you your development set. So with those 60 and 20, right, you can do whatever you want. You can play around with it as many times as you want. You can make as many mistakes as you want, right? But then that last holdout, that last 20%, which comprises your total 100% if you add them all up together, will give you your test set. And that one you do not touch until you are certain you've run all your experiments, you're ready to proceed, and now you cannot contaminate it. But if you do mess something up earlier and you touch that other 20%, I'm telling you this all in the perfect world in machine learning modeling, right? That last
Yeah.
20% you do not touch until you are ready to pull the trigger at the very end. But in most coursework, you'll see that they only do a two-way split, which just goes like 80-20, 80% train, 20% test, and that's it. So if you mess up, you've already contaminated the test set. When I say contaminate, I mean you don't want to use anything that you've learned from the test set to go back from the future to go back and influence your model because now you didn't do a proper scientific experiment. You know what I mean? I don't know. In Excel, there's a lot more work involved in doing that than you would do it in Python or R because you have to select somehow randomly. You have to calculate how many rows is going to be, let's say 20% of your data, for example. Again, this is an example, 80-20, you can do 70-30. You definitely want to allocate most of your data towards training, right? So 60, 40. If it's really small, you really want to give it 90%. Well, that's really high, but 80-20 is a classic one. But again, if you're working with very minimal observations, and I mean like under 1,000, then you don't want to do a holdout set. Okay. Um, I mean, I know some of the stuff that I have gone over was a bit chaotic at times and maybe quick. Um, whereas the initiative may be appreciated by some, it may feel like it required more planning or there's a bit of a frenetic energy to it. But what I say to that is it's very difficult to cover all of this in a 3-week course, right?
Yeah.
And that's why I recommend that you go back. I try to put as much into it as possible up front so that you can go back, pause, rewind, maybe play it slower. Because I
Yeah.
don't want to miss anything. I want to make sure that I cover the scatter plots, labeling the axes. You'd be surprised how many times people just cannot wrap their heads around what a y-axis is versus an x-axis, and they always confuse where the dependent variable goes. The important thing for this course, more than anything, is the setup, right? You have to define very clearly what are your x variables, your independent variables. Once you've defined what your independent variables are, you have to define what is your dependent variable. Maybe even that goes first, really. What are you trying to predict? What is your why? Dependent. And when I say why, people think the question why. It's what is your letter Y, the dependent variable. What does it depend on? Those X variables. So you need to make sure in a multiple linear regression model that this data is quantitative and continuous for your dependent variable. Why? Otherwise, you cannot build a multiple linear regression model. The regression model depends on continuous values like price, age, miles per gallon, uh, revenue, income, so on and so forth. If you're not doing that and you're trying to establish, is someone going to purchase something or not purchase something? That's a binary classification model. That's a yes or no. That's a 0 or 1. 0 for not purchase, 1 for purchase. That is not no longer a linear regression model. That is no longer part of what we're covering in this class. That becomes, at a minimum, a logistic regression model, which starts to go into machine learning more. And I don't think you can do that in Excel. And if you can, it's not even worth it. I would just go straight to Python or whatever programming you use. Yeah, because you can only really use Excel effectively, should use Excel for, I would even argue, kind of try to avoid using Excel long term. But what this is great for is if you are trying to build some predictive models, entry level, um, for even up to several hundreds of thousands of rows of data, you can. I actually don't know how long that would take. I've never run it on large data in Excel, but I would imagine because there's more rows, it would slow things down. I don't know. You can try to use Excel for some basic entry-level predictive multiple linear regression models that would be pretty effective in meetings to draw some insights from quickly. And then from there, you can decide with your stakeholders how to scale. Maybe you need to transition into a coding environment to build some deeper models with it. Maybe the decision is too specific on what's the price exactly. Maybe I just want to see if are people purchasing these properties or not. What, sometimes you can't just leave it to one model. But for this course, again, the important thing is to cover how to plot those scatter plots correctly, where your y-axis is your dependent variable and your x-axis is changing from one graph to the next. It's your first independent variable, then your second, but your y always stays the same. And then how to create a summary output table using the data analysis tool pack, which has within it what you need to see your statistically significant independent variables versus those that are not. That's what R squared measures. How much variation exists between X and Y throughout the data set. And the adjusted R squared, again, is adjusted because you're looking at several independent variables. And understanding really what is a single linear regression model versus multiple. Single just means you're including only one variable X against one variable Y. When you start introducing multiple independent variables, X1, X2, X3, and so on and so forth, now you have a multiple linear regression model. That's the only difference. That's it. So if you can understand that, and then one last thing is a matrix of all these correlations that we just went through are, the reason I showed you how to do it by hand is to show you mechanically what the step is, and also to kind of pivot away from that because you don't need to calculate for each one like this manually. You can create an entire matrix of correlation values for all of the data that exists. And from there, you can see what is the correlation? Is it high or is it low? What does it tell us about the relationship between these variables? And B, to take it a step further, is there any multicollinearity within the data? And that's when any relationship between the independent variables themselves is above 75%. That we'll use that as a threshold for a strong correlation. Or if it goes in the other direction, negative 76%, and so on and so forth, negative 0.80, something like that. That means it's very strong in the opposite direction. So if that's the case, you can create a synthetic variable to multiply those two together wherever you found that very strong relationship. Theoretically, you could do that and rerun the model, but I've in practice never done anything like that. I've never been asked to do anything like that on the job. So it's an interesting technique, I will say. And then just do a write-up at the end, explain your model, explain what you've done, explain what findings you yielded, and that's it. There's definitely, for those that have not done it before, a ramp-up period to kind of establish the heuristics of the practice. And then once you have it down, though, it should start to make sense. For me, it was difficult in the beginning, but just think this way. These are linear models because you're dealing with lines. I know it sounds silly, but it's the truth because you're fitting a best fit line to this random scatter of data. And when you're doing this best fit line against one observation, let me be careful when I say that. Observation means row. When you're doing this random scatter with respect to one variable X and one variable Y, you're looking at a single model and you're trying to fit the best estimate at the prediction, which is an equation for the line. That's your prediction. So that Y equals mx plus b, the slope and the intercept gives you that predictive equation, what your new Y is going to be, right? For that single relationship. But when you're introducing more of these scatter plots together and you're trying to fit that line, trying to establish linearity, that's why it's called linear regression, you're now fitting multiple linear regression models and bringing them in collectively into this summary output table to determine like what's the overall picture of the variation, what's the overall picture of the statistical significance. And it would also help to kind of, it doesn't ask for this in this project, but it would also help to establish a hypothesis testing framework, much like you did in the previous course. What is your baseline? What is your null hypothesis? And that will tell you which direction to go with the statistical significance. Because statistical significance will be used not just in predictive modeling, but everywhere. When you run numbers and you look at the difference, well, I don't know, are the differences in the distributions, for example, between one race and ethnicity and another race and ethnicity, different, statistically significantly different. And you would pick a test. It could be a one sample two sample t-test, and so on and so forth. And you can get into the weeds of all these different kinds of advanced statistical tests, but ultimately you're always establishing whether or not your P is less than alpha. And if it is, then you reject whatever. So your initial claim would be there are no statistically significant differences between this race and ethnicity and the next one. And I'm saying this from practice because predictive models that involve race and ethnicities, ultimately, that's what they want to look at the results later. It's not just about the performance of the model. It's also, did the model perform equitably across the different demographics? And it's not just race and ethnicity either. It's also involves age, sex, sometimes social vulnerability index, and so on and so forth. And you want to see across these sensitive attributes, are there any statistically significant differences? So if you're saying that there are not, but the p-value is less than alpha, then you would say, well, I reject the null hypothesis. There are statistically significant differences. I mean, it's not proof, but it points you into that direction where there's a more of a claim to make that there are statistically significant differences. So you would. So it's not just important to bring, the reason I bring that up, it's not just important for the variables themselves within the model. It's an important practice just to establish, if you're looking at two distributions, how would you know? Just because you can't make a claim just because the mean on one distribution is higher than the other, Well, then you're just discussing skewness, right? Because the median is lower, or the mean in relation to one sensitive attribute is higher or lower than the other. Yeah, you wouldn't know unless you run a statistical test to see if the differences are statistically significant. That's why it's very important to understand what you learned in the last class, P versus alpha. And in this class, um, you're just looking at the predictive modeling side of it, where again, you're still looking at statistical significance, but it's just with respect to the variables themselves. Um, and you can argue that if you have non-statistically significant variables, that they may not necessarily belong in the model. But would I personally pull them out? I was learned a while ago not to just pull anything out of the data set just because of math, because I hate to say in the real world, quote unquote, but really in practice, right? Um, as much as you want to do something, the stakeholders will tell you, no, 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 that's not like in medicine, right? That's not clinically relevant. We still want to see those in the model, but they're not statistically significant. So what? We're putting this into production, and it's just for the long haul. We still want to keep it in. We want to still train on that. So even though you have your math to back you up, it's not always going to be something that wins them over necessarily. But it's good that you have that input. Absolutely. In this 3-week course, it is impossible for us to ask you to build an end-to-end pipeline with an entire perfect model that looks through all the possible cases. And because this process is iterative, you don't just build a model once. This is what people learn in school. They build it once, they submit it to their professor, and they call it a day. They wash their hands clean. No, it doesn't work like that because it's iterative. You build a model, they say, let's take this out. Let's look at that instead. No, let's put this in. Let's look at that instead. No, you know what? The linear regression model wasn't working for us. Let's try a different, but let's still keep that in. Let's try. You'll be going through meetings like this for months, and then eventually you'll settle on some, maybe several models. You'll pick the one that performs best, and then you got to think about something completely different when you have to future proof it when you go into production. And by the way, I forgot to mention something. Just for this class, you're all doing great. It's just the basics. Well, for some, it's still the basics, but if you can learn this, you have to understand what the y is, what the x's are, and that the coefficients that you're putting on these variables are your weights, because that's what they will be in your logistic regression model. And any other model, it's y, it's always going to be y versus x, y versus x. So it doesn't matter if you're looking at binary classification or linear regression. The only difference is the continuity of the dependent variable. And one thing I want to mention is please do not make the mistake of including both. Like if you transform the variable, do not include the original and the new one, because what happens then? You're including the same variable twice, especially if it's x, because you can only have one y, right? Per experiment. But if you're including multiple X's of the same just a different representation with a different scale, it's really the same variable. And your model is going to perform amazing because I have the original X, now I have the log scaled X. Well, duh, it's
Yeah,
going to perform better. You're overfitting it with the
right.
same. So yeah, do not overfit. So always try to clean it. So once you don't want to have the same thing. And you also don't want to include your Y as part of your X by mistake, accidentally, because then that could also overfit it.